great example using like Python, and we'll see. Okay. So thank you very much, Suya, for being with us, and I give you the mic.
Thank you, Bilal. That was a very warm welcome. I guess I don't need to introduce myself again and save everyone's time here. So we are going to have a look at ARM Forge, which is the name for this the suite that has all the profiling, debugging, and performance report functionalities, tools. So today, apart from me, there will be another colleague of mine, Ryan, who will be joining us towards the end of this session for a Q&A. Once again, the overview is going to cover DDT, which is a distributed debugging tool, MAP, which is a profiler, and the performance reports. And yep, we will be covering a little bit of overview quickly in the beginning before going on to the tools, and then in the end there's time for quick demos. So let's get on with this. So what is ARM Forge? ARM Forge, as I mentioned, is a collection of the three software tools we have: DDT, MAP, and performance reports. Now, a little bit of a background. It was basically Olinia, as you must have seen in Bilal's presentation. It was Olinia performance reports. So originally it was Olinia, DDT, MAP, and performance reports. And basically it was let's say a toolkit for HPC application developers. Now it is available on over 65% of all top 100 HPC systems, and it's designed in a way to maximize the efficiency for best of your applications. Olinia was taken over, was merged into ARM in 2016. So from then on, the tools are named as ARM Forge and ARM DDT Map and Report. So the theme of how we design and develop our products has always been to keep the trust of the community, the HPC community, and therefore we have tried to build the tools directed towards all the architectures and not just ARM architecture. So carrying forward the legacy from Olinia, the tools are Forge tools are architecture independent, and they can be used on any architecture. Also, we are always working towards aligning ourselves with the upcoming architecture, if there are any. For now, we don't see any foreseen change in this. So yeah, we will continue to support cross-platform. Yep. So the whole suite is can be put into two packages. We have code generation package, which has the compilers and performance libraries. We have the other package, which is performance engineering, that I said is for any architecture at any scale. Together, that's the ARM Olinia Studio. But there's a catch here. The code generation package is architecture specific. So if we want something that is independent, that's ARM Forge for measuring the performance, for debugging. But if we are looking for performance libraries, then it is specific to ARM architecture only. So talking about DDT and MAP, both the tools, they are fast and very powerful with a very easy to use graphical debugger, graphical interface. And we have tried to provide complete solution for finding and fixing problems on single thread or multi-thread, thousands of threads. It includes OpenMP, parallel, so MPI, all the flavors of MPI, then all the heterogeneous softwares that are written for GPUs, or even hybrid codes that are MPI with OpenMP or MPI with CUDA. and it can brute force all these codes into revealing tricky memory leaks and bugs. So because Forge is available on such vast variety of or majority of the top 500 machines, it has to have this functionality to cater to all the libraries and hybrid software solutions. Now, we have tried to keep this as a low overhead solution. So both DDT and ARM, DDT and MAP are very low overhead, working in parallel. And they show you obviously visualized performance data, even in 3D for when you are, let's say, debugging the arrays. And the interface overall is quite intuitive, user-friendly. As Bilal mentioned, for the performance report, it's easy to read. And also in the other tools, the GUI is very intuitive. It's one of the strongest aspects of ARM Forge suite. Performance reports, yeah, they are something where you don't want to get involved with the GUI, and you are just looking to leave your code running overnight or over the week and just keep getting reports either at the end or maybe even at certain stages. So that is also possible. And you'll just have an HTML file or any other, there's another format, JSON. So you will just receive it in your email or even in your working directory. So performance reports, it analyzes most of the metrics that are available within the GUI, and mostly the important ones like the CPU performance, CPU functions, memory, IO, and hardware counters for code optimization. So these are all present in PR. But yes, of course, every single tool from the GUI is not, or every single functionality is not going to be available. But yes, if you are doing constant optimization of your code, then PR is really helpful to have it next to your code. Just look at the suggestions that are provided and make changes in the code. So what are the different ways in which you can use ARM Forge? So where is the first question is, where do the tools need to run? Well, answer is essentially wherever the software is running, wherever the application is running. Typically, that will be the compute node. But then what about the GUI? Because you are going through a tunnel, you are hopping over a login node. So there may be a case that there is no interactive session it's allowed, or the X forwarding is X11 forwarding is not available, or it becomes really slow. So then the solution had to be designed in a way to not get stuck with such a in such a scenario. And to provide flexibility, the GUI can be launched in different ways. So we can use offline mode or interactive mode, which is going to come through your head node or the login node. So in the offline mode, again, you'll have the code running in the background, and a report in HTML format or text format will be available in your working directory. In the interactive mode, you launch it from your login node, but yes, it is accessible remotely. So you are at your laptop. You can have a remote client that will access your compute node via the login node, and using some flags such as -- connect or -- reverse, offline, you just are able to access the GUI in your laptop, getting data from the compute nodes. So the heavy lifting that the GUI has to be updated all the time, that is bypassed, and just the sampling data is coming from the compute node or through the login node to your laptop, whereas the GUI runs within your laptop. or your workstation or whatever system that you are at. So it could also be you working on an AWS cloud instance, EC2 instance on your laptop, and that is making a connection to your university system or your institutional infrastructure. So to launch Forge, you can simply write Forge in your command line. But let's say if you're looking for a debugger, then DDT, as we said, you can just write DDT and go ahead with your regular command. So MPI run or srun with the file system and the application. Again, if you are using remote, you are running the software on the machine, but the GUI on your local client, then dash dash connect will be the flag that creates the tunnel, the connection. And again, as I mentioned, offline will provide you with an HTML file. So you can see for offline mode, we prepend with dash dash offline, and yeah, in the report underneath, we have details for every line. So you can see there are stacks. It also tells you the breakpoint at line 50 and gives you the information from underneath. And yes, sorry, this is the general GUI for DTT, but we'll cover it quickly going ahead. Similarly, for map as well, you just have to write map and dash dash connect if you are using remote or reverse connect functionality. This is the general GUI for map. So you have the memory usage, you have call duration, you have CPU floating points, you have your source code, and there's more thread activity stacks available. So we'll cover that quickly in the coming slides. Also, we have a dash dash profile option, which creates a profile non-interactively. So you don't have to use the GUI, you just use dash dash profile, and the profiled output will be saved in the working directory, and you can access it later, or it can be transferred, it can be pulled in through any other method. If you do not use any of these flags for DDT or map, you just are going to get the GUI, and we call that as express launch. So just write Forge or DDT or map in the command line, and boom, you have the code, the software. So once again, these are the performance reports, and the data is formatted in a manner that is much more comprehensible and makes it easy to picture the computing scenario. So you have CPU, MPI, I/O, threads, everything. So it's including all the important aspects, and yeah, highlighting all the statuses of memory and I/O. So it can tell you that whether the operations are running memory bound or compute bound as an overall conclusion, and with a suggestion that what can be done to improve the system. These are the links to our web pages where you have the developer .arm.com for all the resources. So we have a user guide. We have also another link for development tools, and there you will have case studies, you have tutorials, you have pre-recorded sessions, so the webinars, and then there's even more tutorial files available. And we have the download and installation from the developer, again, the developer webpage, where you can also see the release history for every sub-release. And again, this is the email to reach us for any query after this. quickly. So you must some of the audience mentioned that they use GDB instead of printf or the clock functionality. So DDT is based on GDB, but the difference is it's not just you know, it's providing more than just an interface. So on the right we can see an alternative to GDB, which is DDD, and there are many others. There are like 20 others, and they're all open source, but there are more or less graphical interface to GDB. They're not providing any any level of analysis or any more sophistication to the performance of your code. So DDT is more than just a GUI or an interface to the fundamental GDB. Yeah, quickly, when we are looking for debugging, so the basics that are that always remain the same is that you try to find out what went wrong. You try to collect data between your loops or other functionalities or function calls, and you try to isolate the problem. You try to make changes and repeat it until you have found out the bug and you are able to move on. DDT, on the other hand, because it's based on the fundamentals like who, where, how, and why, it tries to enable these questions, and it tries to find out the problem by forcing the code to crash, and in that crash it gathers all the information from variables and array values, and collecting all the communication data. So if you can see at the bottom, there are the MPI ranks, and we have the line graphs that tell you the details about at what line there is a communication failure. So the line graphs basically are for the process ranks, or let's say thread indices that are there in the code. Now, it has a lot of it has very high debugging capabilities, I would say, as a HPC researcher myself, that has relied mostly on Valgrind, and at the very most going to GDB. DDT has very high, literally very high, very strong debugging capabilities. So you can work with visualizing your arrays in 3D. You can, and this is also quite helpful when you're working with machine learning codes. Also for let's say CFD, where MPI is predominant, you can have a look at your MPI ranks and how they are communicating with each other. So you can see on the right we have the communicators listed, and at the bottom you have the queue and the communication between all the instances ranks. And yeah, there's even more to this. You can export the data, you can see the statistics, the standard deviation, and stuff like that. This is the how the GUI looks like. So you have the source code here, you have the MPI ranks at the top, you have a lot of controls there, and you have the options to get in and get out of the code. You have the disassembler view 1001. You have the variables on the right that are local variables, and you can also see the values information for current lines and stacks. At the bottom, there are if you are leaving. So in the red, we have the breakpoints here, and whenever you start to debug, DDT stops at the first breakpoint. But then you can also use trace points, and they will all be listed underneath here, besides having breakpoints and watch points. So you can see all the three here. We also have the version control capability, so you can see line-by-line information from Git, or if you're using Mercurial or Subversion, it's all possible inside DDT to keep a trace. Also, the disassembler view that I mentioned, the 1001 at the toolbar at the top. So for the developers that are optimization focused, this provides an insight. It's like the values coming from directly from the hardware, from the assembly code. We also have memory usage. So for each MPI process, you can examine the memory status across these processes over on the right. So overall, and for each process, you can restrict to 4 or 8 processes, and you'll have the pie chart and also the value for other things in a statistical manner. You can also quickly, when you're launching DDT, you can quickly say what kind of memory debugging you would like to have. So there are a few levels, fast, balanced, and thorough. And they all have so if you're thorough, it makes the debugging slower, but then you'll have a lot of information about your memory usage, communication. You can also set guard pages that blocks your the start and the end of your memory stack. But then it takes memory. It in itself consumes memory, so it's memory intensive, we can say. To launch DDT, you have -G and -OO flag whenever you're launching it. So I'll quickly just jump to how to launch it. DDT, offline mode or reverse connect, and going on with srun, MPI run, MPI exec the same way. If you are doing it in Express Launch, you have the screen, you have the first window, you can just run, and or you can attach to an already running process. We have the remote launch. We can configure it to connect to remotely to a system, a remote host. Yeah, when you press on run, you have to select the application. You can pass the arguments. You can select memory debugging, CUDA, and yeah, you can also change your MPI version that you're using. In Remote Connect, I will say quickly that you'll have the configure window from remote launch. You can provide the host name, the directory for the Forge installation, your password, and you will see at the bottom the license that is there on the compute node. And yes, from remotely without X forwarding, X11 forwarding, you will be able to use GUI as if you are running live. Yeah, so DDT srun will simply launch Express Launch, but if you're reverse connecting it, then DDT -- connect srun the same way, and yeah. The offline mode, as I mentioned, provides output report in HTML. You can pass memdebug flag instead of, if you're not using the GUI, obviously in offline mode, then you can provide flags that will yeah, provide you information on memory leak or seg faults, etc. This is how the HTML file will look like. I already pointed out in the previous slide. For Python, you'll just have to provide additional flag, Python 3 or linear Python debug, and your Python script. If you're using a batch, then it will be srun the same way, everything else remaining the same. For CUDA, the flags will change a little bit. So when you're debugging, it's -- CUDA RT, shared, small g and capital G both. And yes, you'll have the window where you can select CUDA and run. If you want offline, then again, it's -- offline the same way. I'll just run over a quick example for debugging. So let's say you have encountered a seg fault, and I'm sure all of you are familiar with this in your Linux environment. But what if you're using DTT? What are you going to see then is something like this. So it will highlight, it will stop at the line where there is the fault, so line 103, and it's going to give you the exact reason why this has happened and what has happened and why this has happened. So the address is not mapped to the object. We can observe on the right-hand box that we are trying to access X and Y for array called tab, but X is, absurdly large. So while Y is 0, and that's creating a fault. Memory address that is not actually mapped. Now, just by hovering over the element, it gives us more detail and the size, etc. Right, so quickly moving on to map. I have very little time in my hands. So what is map? It's a profiling tool. It uses sampling instead of instrumenting or tracing or tracing. So that way it's non-intrusive, and it has very little overhead, whereas still maintaining accuracy. So what you guys do with printf or the clock commands is called as instrumenting. There are even more. That's the most basic instrumenting we can say, but there are much more complex tools available. But obviously they slow down the whole thing. So in sampling, you automatically collect the data, and it's non-intrusive. You can see different kinds of output. So if there's a hotspot, that's good. So the graphs are they're basically representing the execution time. Then this is the best case scenario. In green, spike is what I'll say is more realistic to our code, where we may need to work on the algorithm to exhibit the path of code, more friendly. So depending on the number of spikes, and the optimization time is variable, whereas in the flat, it's the worst because the amount of time you'll spend optimizing the algorithm is going to be huge, and there will be very little gain from this. So we don't want a code like that. We would want to sit somewhere in the spike. Yep. So map is sampling based, has low overhead, easy to use, and the results that it shows are very comprehensive. And yeah, we'll move on to how to launch map. So instead of DTT, we just replace it with map -- profile, and yeah, your application with the -G flag. This is the basic GUI for map, and you can see again, there's a source code, there's main thread activity, there's a floating point, and memory access for CPU, memory usage. At the bottom is main thread stacks. We can access more metrics that are available in the metrics over here. And yeah, at the bottom is the functions view. Now, there are some more metrics available that can be activated for MPI and CPU from the metrics tab. We also have the option for perf metrics that are collected from your OS, and yeah, there are lots of options there for cache misses, for L1, L2, L3, literally hundreds of options available. So you just have to activate it, and yeah, these will be shown in your perf report or even in your results in the bottom. There's also caliper functionality. I'm not going to go deep into it, but yeah, we can cover it later or some other time. Right. So basically, sometimes we can see a large overhead, and this could be resulting to memory access consuming a lot of time, and this is not good. What we need to do is we need to make changes of how we are accessing. So if we are having a temporal locality or spatial locality, we need to make sure that the data is not too distributed. The loops are, the stride is maintaining the temporal locality. So we can see the loop here, and we can see that the time is shown 55.7, and the way we are traversing in this loop is scaling the locality of the data. We have a very little floating point performance. So we make a change, we transpose the matrix, and we see that the result is different. In the dark green, we have single thread computation. In the blue, we have MPI communication. In the red, we have memory access, and I/O is not visible clearly, but at the very top here in the orange is I/O. Yeah, so we can see by transposing, we have a higher vector floating point, and we have also seen the same at the bottom. We have a 55% for MPI now, and yeah, the main thread activity shows clearly that we are more efficient with time, 10.7 seconds. Again, for improving your I/O bottlenecks, we may be, wasting time on the wrong functions. We may be writing data inefficiently. So if we change that, let's say here we can see that we are writing the file inside the OpenMP directive. So previously we have a very high bottleneck, I/O bottleneck, and the time is 250 seconds. You can see 69%, whereas now we are down to 4% and 28 seconds. So yeah, by making changes or by making your code efficient, you can overcome the I/O bottlenecks that are clearly highlighted in map. We have already covered that, so I'll just go over to performance reports quickly. And yeah, so you can see that again, because performance reports is running the map tool behind in the background. Therefore, it is basically map, but not using any GUI, and with a smaller set of tools, but the ones that are necessary. So we have I/O, MPI, OpenMP, and memory access. Again, for performance report, you just have to write perf report, MPI run -np8 and your application. It's available in 3 formats: text, besides HTML, text, JSON, CSV. And if you already have generated a map session, then you can also just straight away say perf report, take out all my important data from the profile session and give it to me in XML or HTML. So once you have performed an optimization, you can see that we have changed the MPI, and the time has reduced. So we are able to parallelize the code. We are able to distribute it better over the resources, like Bilal showed in his presentation. The time just came down, and the flops increased drastically. So it's something like that, but it is also showing the difference very clearly in terms of memory access over here and here. Right, so I will jump to the map window. This is a Python code. I had already put it open for visibility. I'm not sure if a lot of you are using your laptops, if the screen is going to be clearly visible. But yeah, come on. I will stop share and reshare my screen quickly to switch between my monitors.
No problem. We have a question by a colleague that he is asking about yes, when we get a profile data where application is combined with Python and precompiled binary. So is it
Yep.
possible, or is it only about the Python part, while the binary will be very difficult? Is it correct, or can you please elaborate on that?
So this precompiled binary, you're saying that it's not Python, it's
Eventually.
Yeah, we can so
Okay.
I'll show you. Right, so I compiled my profiles, my Python script, and you can see it here. And all I had to do was just give the command map Python as we saw. And so what we saw was for debugging, which was all linear Python debug flag, but I'm profiling here, so I'm not using that. And we have it straight away. I'll close this and show you one more time. Yeah. So I already have the profiling sessions here. So I can also, like I mentioned, I can launch the sessions, or I can reprofile. And yeah, so let's say I can change my argument. This is a Fibonacci, so I'm just putting the numbers that it has to find.
So you can see you have you don't modify anything in your Python. You have
Yes.
just one. You add just like one command line. That's it.
Yes.
And this will work both on Shaheen and Ibex, as I shared it in the
Yes.
comment.
Yes.
And it will be the same eventually also, but he will share with us for the part like with the calling on GPUs.
Yes. So I'll show you right after this one. So we can see here that we have the main thread activity inside. So this is from left to right. This is from time 0 to your final time, which is 6 seconds approx. And at any instance, you can see in pink, we have the Python interpreter. So the instance where my mouse is right now, 100% of the resource was utilized in by the Python interpreter. But if I go in the green, all of it was utilized for computation. Also towards the end, I can see the same. And it also highlights for individual, the line view. So there and over here, one sec. Yep, so you can see more details about your floating point operations, integer operation, memory access, everything. And at the bottom, you have the functions view. So it's very detailed. You have the IO, which we already saw, main thread activity, and yeah. it's a very it's a basic example. It's not a giant weather modeling application. I wish I could show that more comprehensive. But if you go in the metrics, you can change things that are visible. So this is the memory access for you at any instance, and we can see by hovering. Come on. I can also select between. Yeah. So it shows me overall memory usage and also the activity individually. Then we have yep, for node as well. The same is available for your compute node. And if you're using MPI in Python, so all the MPI calls are available. You also have overall application activity, which we don't really chase. Then your float, your integer vectors, most commonly used in most of the Python codes. So not there here. For larger, let's say if you're working on Shaheen with a huge code, we were getting these questions a couple of years ago for energy usage and especially with GPU. So that was also added at some point, and now we have this. Okay, so yeah, I will switch to CUDA code. Let's say come on. Right, so yep, I have the CUDA executable with me, and all I need to do is let's say if I launch map straight away.
We have a question. Yes, it should support. Does it support MPI for Pi?
Yes, it does.
Okay. And the second question, like how we can check whether AVX2 or AVX 512 is used?
I think I can come back with that with an answer to that because I know how to do that for ARM architecture when we use SVE2.
Okay.
But for AVX, I'm not sure. So I can come back with that answer later.
No problem. No problem.
If that's not a problem.
Yeah, sure.
Yeah. Right. So, oops. I'll just load it quickly. I'm wasting time. So, yep. I'm sorry. Let's go back. Okay. Yeah. Got it. Right. So we just have to, so this is Express Launch that I'm demonstrating. You have to select your application. You have to, you can also stop and analyze. You have to give your working directory, and yeah, it will automatically identify a CUDA code, and we will see that there's a special tab available for CUDA applications. Right, so it shows GPU kernels at the bottom, where it tells you the details, line level information for the kernel. If I go to metrics, and if I select NVIDIA GPU utilization and metrics, NVIDIA GPU mem usage, yeah. So if I select anywhere in between, yeah, this is it. And I can see that this is my kernel and functioning. And I have block indices in 2-dimension for row and column. If I am checking my multiplication, so I have this is in serial. This is not using my device. Inside that, inside my kernel, I can go in and yeah, sorry, it was in the wrong function. For memory, when you're bringing it back to the host for initialization, so you get the details by selecting your line that is shown, and in the main thread stacks, you can also see the lines in hierarchy with the highest memory usage, with highest computation percentage. You can also dive in individually for which loop and which line. So you have the memory access information here for this line, and for the other one, we have the scalar integer value and memory access again. So these detailed values are available through the main thread stack. And again, the GPU utilization, what you see, the value is an overall averaged over 11 seconds. But this program is not using streams. So I'm going to show you another one, which is using async functionality with the async mem copy, and it creates streams. So in this case, in this one, it's a general host to device, device to host, and yeah, mem copy and the kernel in 2-dimension. It's quite straightforward. Yeah.
So yeah, can we let the last demo at the end? So we have like an yellow, okay. And then okay. Like we can follow up with more question and the last demo with the stream. You can accelerate, so we can say.
Yeah,
and
it's
here
just
like
5-10 minutes of stuff left. So
okay, no problem. Okay.
Yeah.
Excellent. Thank you very much.